Hello students, myself is Mr. Sanaullah Khan, PGT Physics from NCMS Jaipur. Today we are going to start 12th Physics, first chapter Electrostatics, and the topic is electric field. What is actually electric field? Let us discuss about it. Electric field means if any charge is placed in space, it has the ability to apply force on the other charges. There is a criteria for applying force of that particular charge. That criteria, that region or that space is called its field. So we can say that in a simple sentence, simple language, a region around a charge where its effect can be experienced. So let us write in simple sentence, a region around a charge where its effect can be experienced. This effect may be in the form of force. We consider that there is a source charge in space. That source charge at location A here is considered to be capital Q. If we place any charge here at location B, that is small q, then this charge may experience the effect of the source charge. What do we understand by the source charge? Source charge means that the charge which produces its field, electric field. And in order to test the effect of this source charge, we bring another charge there in the space, in that region. That charge is called as the test charge. So capital Q is a source charge which produces electric field, and small q is a test charge which is experiencing the effect of the source charge. Now here we can say that if suppose small q is placed at this location, this q is experiencing force here. If I place small q here in this region, and at this location I consider C, here also Q will experience force. If I place this small q here at the location D here also Q will experience force. But small q test charge has constant magnitude. I consider small q is of 1 coulomb charge there. But force at location B, location C and location D will be different. At C, it will experience more force. At D, it will experience less force than the location B. What is this? This is generally the intensity of electric field at different location. At C, the intensity of field created by the source charge may be larger. At D, the intensity of field created by source charge may be less for test charge. So what is the intensity of electric field? So we can write here intensity of electric field due to a source charge at a point is defined as the force experienced by unit positive test charge at that point. Without disturbing the source charge. What is the meaning of without disturbing source charge. It is very important to understand this, students, because when we take any test charge in the space in the region of source charge, the magnitude of this test charge should be very less than the source charge, so that the source charge will not be disturbed by test charge. This is the condition for without disturbing the source charge. Otherwise, test charge will create its own field. When it creates its own field, then the field created by the source charge will be disturbed and it will move from its place. Okay? So this is the definition of the intensity of electric field. Intensity of electric field is denoted by E here. E is equal to, we can write limit Q test charge tends to 0, force per unit charge. This is the formula for the intensity of electric field. We can write this as in vector form. Intensity of electric field limit Q tends to 0, force per unit charge for the electric field. Intensity of electric field is a vector quantity. It is a vector quantity. Then what is the direction of electric field? Its direction is along the direction of force. Suppose that a test charge is placed at a particular location in the field of source charge, and test charge we are taking is a unit positive test charge. Source charge is also positive charge. There may be the force of repulsion takes place in the test charge there, and it will move. The force is applied in the opposite direction, and the direction of the electric field will be also along the direction of applied force. So we can write that its direction is along the direction of force. Now let us see the SI unit of electric field. How do we write the SI unit of electric field? But the formula of electric field, intensity of electric field, force per unit charge is there. So we can say that the SI unit of E means electric field. For force, we write the unit of force is Newton, and for the charge we can write Coulomb. So we can say that the SI unit of electric field is written as Newton per Coulomb. Then what will be the dimensional formula of electric field? So let us take out the dimensional formula also. Dimensional form of electric field. Of E, we can say that dimensional formula for force is what actually? The dimensional formula of force is mLT to the power minus 2, and here we have got charge Q is there. Dimensional form of charge is A into T, ampere into time. We write here A into T, ampere into time, and if we take it up, we can say that the dimensional form of electric field will become mLT to the power T to the power minus 1 into minus 2, minus 1 minus 2 will become minus 3, and this A will go up, so it will become A inverse. This is the dimensional form of intensity of electric field. So this is about the intensity of electric field. Means the intensity of electric field may be weak also, strong also, according to the location of the test charge in the field there. If test charge is away from the source charge, there may be the weak electric field. The intensity is weak. If it is closer, the intensity may be stronger there. Let us now see that The electric field due to a point charge. We try to find out the electric field due to point charge. Our next topic is electric field due to a point charge. Due to a point charge. Now we are taking a point charge here and we have to find out the electric field due to this point charge. We can find in a simple way also by considering a source charge and test charge. There may be some distance between the source charge and the test charge, but I want to take this in a coordinate frame. So let us take the coordinate frame for this. X-axis y and there may be z-axis of this. This is the origin here. We consider a source charge q at origin q and we consider one point p here in the coordinate frame. The distance of the point p from the origin is considered to be r. We assume that there is a test charge at point P, Q naught. Q naught is the test charge. We have to find out the electric field due to this point charge which is placed here at the origin. Okay. So what do we see here? There are two charges now. The source charge is Q is there and test charge Q naught at location P is there. We have to find out there may be the force because two charges are there and there is a distance between the two charges and the distance is r. So we apply according to this condition, Coulomb's law. What will be the force between these two charges? So according to Coulomb's law, the force between the charges may be constant k into q naught upon r square, and in vector form also we can write the unit vector r and this is the force in the vector form like this also. What is k? K, you know that you have already studied the Coulomb's law. K is the constant 1 by 4 by epsilon naught. So we can just extend this term as force F is equal to 1 by 4 pi epsilon naught q naught upon r square into vector r. This is considered to be the equation number first. We consider equation number first. Now, test charge is Q naught, and earlier we have seen that the test charge, the electric field per unit charge at point P is what? So we can say that we already discussed the definition that what is the intensity of electric field at point P where the test charge is there. Intensity of electric field or electric field is force experienced by the test charge. So we write electric field at P is considered as E is equal to limit Q naught tends to 0 force per unit test charge. Okay, let us consider this is equation number 2. We apply the value of force F in equation number 2 here and we try to find out the electric field here. What do we see there? So putting the value of force in equation 2 here. So from equation 2, what do we get? Electric field E is equal to limit Q naught tends to 0. Then force, the value of force will be here 1 by 4 by epsilon naught q naught upon r square and unit vector r. Q naught may be cancelled here. What is left out here now? So we can say that electric field E is equal to here 1 by 4 pi epsilon naught q upon r square. Okay, this is the electric field due to a point charge. The point charge is where? At the origin this is the electric field due to a point charge. What will be the magnitude of electric field? We can say that the magnitude of electric field is written as E is equal to 1 by 4 pi epsilon naught Q upon R square, and this is the another form for the electric field due to a point charge. Electric field due to a point charge, this formula for electric field is applicable only for the point charges. Now this is about, that's all for the electric field due to a point charge. Now we can simply also derive the formula for electric field due to a point charge by putting two charges there. I already explained to you there. Okay, let us take the next topic. Our next topic will be electric field lines. Electric field lines. Electric field lines are what actually? So we can say that in order to explain the graphical representation of electric field, we require this electric field lines. But these electric field lines are not real ones. They are considered to be the imaginary lines, and this is just an assumption for us. So what is electric field line, or what are electric field lines? We write like this: electric field lines are imaginary, we consider imaginary, smooth curves which represent the direction of electric field. Smooth curves which represent the direction of electric field. Direction of electric field. These are imaginary lines. Now let us discuss about the properties of the electric field lines. We will come to know that the arrangement of electric field lines. Properties of electric field lines. We consider the first property regarding to the electric field lines. For a single positive charge, electric field lines are radially, seems to us outward, means they are going outward from a positive, away from a positive charge there. So we can say that electric field lines are radially outwards. How they are radially outwards? Let us see that. Suppose that there is a positive charge here. Then electric field lines are seems to us moving radially outwards from the positive charge, away from the positive charge, and by arrow sign we can indicate this. These lines are moving away. This is first point for the first property. Second, we can say that for a single negative charge, we consider that the electric field lines are moving radially inward to the negative charges. So we can write that electric field lines are radially inward. If negative charge is here, so we can consider that these are electric field lines, and we say that by arrow symbol we can show that they are radially inwards, moving into the negative charge. Third property. What is third property of electric field line? These are just assumption and these are just imaginary lines. Third property for opposite charges. Suppose that opposite charges are there, then we can say that for opposite charges, two charges are placed. We can say that the electric field lines will emerge out from the positive charge and it will terminate at negative charge. Okay, we can say that electric field lines begins start from positive charge and terminates at negative charge. So symbolically, how can we explain it? We have to take two charges, positive and negative charges there. Suppose this is positive charge and this is negative charge. The electric field lines from the positive charge, it begins from the positive charge and terminates at negative charge. Similarly, we can draw this here also. And in this way, we can just draw the from positive charge is emerging out, means the arrow symbol shows coming out from the positive charge, and here we can consider that these lines are moving into the negative charge, means they are moving inside, means they are terminating at negative charge. This is the third property of electric field lines. Now let us take next one. If any tangent, if a particular point if you take on an electric field line, then the tangent drawn at a particular point on electric field lines shows the direction of electric field. So we can say that at any point on field line, tangent drawn shows the direction of electric field. So suppose that here, if from positive charge the line is moving outward here, suppose that, and if we consider any point here or here, if we consider any point here on the electric field line, if we draw a tangent over here, so this tangent will show the direction of electric field. This is the fourth property of electric field. Let us take next one. Two electric field lines never intersect each other. Two electric field lines never cross each other or never intersect each other. Cross or intersect each other. Why? This type of questions may be asked sometimes, that why the two lines, electric field lines, do not cross each other, do not intersect each other. Suppose that if two electric field lines are crossing each other, they are intersecting each other, then we can say that there may be the two directions. These are two electric field lines, they are intersecting at this particular point here. So from this particular point, there may be two tangent drawn. One tangent may be in this direction, other tangent may be in this direction, and these two tangents shows the two direction of electric field, and this is not possible. So this may be the answer of this question whenever it is asked that why the two lines do not cross each other. Okay. Next property we may take. Electric field lines are discontinuous. They do not form a closed loop because electric field lines are discontinuous lines and do not form a closed loop because they start from the positive charge and terminates at negative charge, so these curves are not continuous. Seventh point we may take here, the electric field lines, if we consider or if we just assume about the number of electric field lines for a unit positive charge, so we can say that for a unit positive charge, number of field lines are considered to be 1 by epsilon naught, and 1 by epsilon naught is considered to be the value of epsilon naught is 8.85 into 10 to the power minus 12, and if we take this minus 12 to up there, it will be larger in number. Similarly, the other properties are there. We can consider that next property of the electric field lines, at one we can say that the electric field lines are seems to stretch or they contract each other, which shows that the force of attraction between the two opposite charges, they contract each other when the positive and negative charges are there, means unlike charges are there. Ninth property we can take for this electric field lines are there. The electric field lines exert a sidewise pressure. It means that there is a force of repulsion between the two like charges. So these are some properties of the electric field lines now. Okay, and I hope that all of you have understood these topics: electric field due to the point charge, electric field intensity, electric field lines and their properties. So in next video we will continue the topic from electric dipole. Till then, all of you stay healthy, stay safe, and goodbye.